All right, another example problem. A gas cylinder holds 0.1 moles of O2, so oxygen gas, at 150 degrees Celsius and a pressure of 3 atm. The gas expands adiabatically until the pressure is halved. Calculate the final volume of the gas, the final temperature of the gas in degrees Celsius, and the total work done on or by the gas. All right, so this is an adiabatic process, meaning the equations we care about are down here. Adiabatic is characterized by Q is equal to 0, so no heat, no energy exchange by way of heat, which leads us with work equaling the change in thermal energy, which is why work is written as NCV delta T, because the change in thermal energy up here is NCV delta T. We also have this relationship that P initial V to the gamma power initially has to equal PV to the gamma power finally. Now gamma is a constant. O2 means we have a diatomic gas. So that means we have gamma of 7/5. So I'm going to come back here and write that. Gamma is 7/5. I write my gamma kind of weird just because I'm kind of challenged in writing my gamma. So the relationship we have between pressure and volume is this. The 7/5 again comes because this is oxygen gas, O2, so two oxygen atoms bound together. The work is equal to NCV delta T, because that is the change in thermal energy. Let's see what else. We know the number of moles is 0.1. We know the temperature initially is 150 degrees Celsius, which we might want this in Kelvin. We'll figure it out. I'll change it later if I need to. We have an initial pressure of 3 atm. The gas expands adiabatically until the pressure is halved. So the final pressure is going to be 1/2 of the initial pressure. So 1.5 atm. All right, we want to find the final volume of the gas first. We have initial pressure, final pressure, but no volume. Okay, but I do know the number of moles and I know the temperature. So if I want to find volume and I know I have a pressure and temperature and a number of moles, the ideal gas law sounds like it might be helpful. So PV equals nRT. If I use initial pressure and initial temperature, this will give me my initial volume, which I can then use that relationship to find final. Okay, so we have 0.1 mole, R 8.31. Initial temperature, we do need to add the 273 because we do need to have the temperature in Kelvin when we use the ideal gas law. So 423 Kelvin, that's what I want to put in here. Over our initial pressure is 3 atm. We will want that in pascals, so I'll put that conversion in there. So I'm just plugging in to get our initial volume. The initial volume, if I've plugged things in correctly, I'm going to take a few digits out. So 0.001157 meters cubed. I need the final volume That's what question A is asking me. I could use the ideal gas law again, because it's true at a final moment in time, but I don't know final volume, nor do I know final temperature. So now that I have initial volume and I have initial and final pressure, this relationship will be helpful. The initial pressure is 3 atm. And you'll see in a second why I'm just leaving it as atm. V initial we just calculated. This has to be taken to the gamma power. That will equal our final pressure times our final volume to the gamma power. So when I divide this 1.5 atm over, these units are canceling. So I essentially am ending up with, 2 times 0.001157 to the 7/5 equaling V final also to the 7/5. The units on those pressures cancel. Had we converted the conversion to pascals would have canceled as well. All right, so to get rid of the 7/5 power, I can take both sides to the inverse of that, the 5/7 power. So this is going to be V final. I end up with 2 to the 5/7 power times this volume. Once I take the volume to the 7/5 power and then again to the 5/7, those powers cancel. So this volume times 2 to the 5/7 power. I'm getting 0.001898. This is in meters cubed because the volume I've plugged in is in meters cubed. So this is the answer to part A. We could put it into liters if we want. I guess we need to look at correct sig figs. 2 sig figs. So 0.0019 meters cubed or 1.9 liters. So with correct sig figs, this is our answer. So part B, the final temperature of the gas in degrees Celsius. Well, we can use the ideal gas law now that we have a final volume. We have the final pressure, we have the final volume. So T final will be P final, V final over NR. We do need this pressure to be in pascals because the R we're using is in terms of SI units. So here's our pressure. Our volume, 0.001898. I'm using a less rounded number in this calculation just to minimize rounding in this calculation. N is 0.1, R. So T final. I'm getting 347. This will be in Kelvin because of the units on R. 2 sig figs, so this is approximately 350 Kelvin in terms of 2 significant figures. Finally, the work. We have the equation for work up here, NCV delta T. Let's just kind of scooch a little bit. We have N. CV, we come back to the test notes. CV This time we have diatomic. Oops, that's the wrong slide. So diatomic, we end up with 5/2 R for CV. So the work will be 5/2 NR delta T. 5/2, N is 0.1, R is 8.31. Delta T, come on. Our final temperature is 347 minus the initial temperature, 423. So the work is I'm getting negative 158. So essentially negative 160 joules in terms of two significant figures. Now the negative, that means energy left this gas. It went to the surroundings. But V final is bigger than V initial. So it expands. The gas is pushing out on its surroundings, so that makes sense. The energy is leaving the gas to go to the surroundings. So all these problems, you want to find what process you're talking about, but we also have the first law of thermodynamics that always applies, so there's a few equations that can always be used, and then we do also need to look at the equations that are specific to the process.